of the session. Now it's recording. Okay, perfect. So machine learning, extract, here extracts. Close, close, close. Le problème, c'est que j'ai pas suivi l'image précise. Okay, so that's the thing. Machine learning and open from here. Ah ouais. Je vais les dire. For the first question, we have the file that we write during the session. So Constantinos will put everything on the web page later. Okay. Okay. So everyone has the notebooks downloaded. Yes. Okay. So machine learning. That's a very sexy subject because it's quite useful for different type of industries. And learning, what is learning? Learning is transforming experience into expertise. Okay, that's essentially learning. And we're going to see how we can transform some learning, which we presented into the form of data, into some expertise for the machine. Okay, so this example is quite useful. You have some experimental data, those points, and maybe you want to create a predictive model. What is a predictive model? It is a function that takes as an argument some value here, x, and will return ideally a value that corresponds to some relation, some physical law, some economical law, something. By the past, statisticians essentially, or other type of scientists, try to find those models based on some formulas like this. This is a polynomial. So you can say, okay, I want to find some function that passes at best through the points. And they invented regression analysis, they invented these type of things. But today with machine learning and specifically with deep learning, the approach is different. Why is different? It's different because the functions you can approximate are more rich, and because of the way you are looking those functions is by probability and optimization. So it's different from classical regression. But the idea is that you want to find a model that tunes well on data to predict new data. Here, you may take something simple like this, a line, a straight line. So this is a linear regression. But it's maybe not taking into account very well the data. So you may attempt to increase the degree of the polynomial to fit the data best. But there might be some problems like this. If you increase too much the degree of the polynomial, you are approximating very well the data you saw, but your prediction power is very poor. Why it is poor? Well, if I take an x something here, instead of giving me a point here, it will give a point there. Okay, so not always having more terms in the polynomial expansion here gives a better model. Okay, in machine learning, this is completely true. It's known as the variance, I don't know, remember, bias and variance trade-off. That's the name. The trade-off. You have a trade-off between the complexity of the model and the accuracy of the model. So we say that learning is transforming experience into expertise. And when a child learns to multiply numbers, usually he learns the multiplication tables. But when do we know that this child actually knows how to multiply numbers? Because probably he just learned, he just memorized the numbers, you know? Like 2 by 3 is 4, 5 by 7 is, I don't remember, okay? But you have this type of things. Memorization is not learning or understanding. And that's the same thing we want to do here. For a child, we pass an exam. We want to test if the child is able to generalize to new cases. And that's exactly the way you are going to evaluate the quality of a machine learning solution. You are going to evaluate the power of generalization. If I give new data that has not been seen before, is the algorithm capable or able to give me a value which is correct? Okay. Perfect. So, what are the typical tasks you have in machine learning? Well, you have classification. Classification means that you give some examples of data, here some images, and you say what's the class that belongs this input. So the first image belongs to the class cat. The second image belongs to the class dog. So if I want to make the computer learn what's a cat and what's a dog, at least from its image, I'm going to give this type of experience. And the expertise I want to get back is a function capable of taking as an argument an image and telling me if there is a cat or there is a dog. Okay. By the past, so by the past means before 2006, essentially, all the people in the mathematical community working on image morphology and this type of things to recognize cars, recognize different type of things for autonomous vehicles, for example, use other methods, old methods, based almost in PDEs, in partial differential equations. And the problem is that it is very difficult to describe what a car is. I mean, in a non-intuitive way, you know. Okay, a car is something, I don't know. Okay? So that's the main problem that machine learning and deep learning solve. You have to use machine learning when it is difficult to program a recipe of an algorithm to solve the problem. No? Typically in programming, you say take x, add 5, multiply by 2, blah, 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 blah. If you are unable to say clearly the steps that the algorithm has to take to answer your question, probably machine learning is a good approach. Another type of task is prediction. You want to predict some value. For example, if you say how old is that person and is this a female or a male, you want to predict the toe of the person. Okay? So for example, a female of 6-year-olds might have a height of 1.15 meters. A guy of 11 years might be 1.48 meters. Okay, you want to predict some value. It can be whatever. It can be, for example, very nice problem. If you have some agricultural land, let's say apples, and you want to predict what will be the production, it's not coefficient, it's or the maturity coefficient, for example. So the thing we do now is you take a drone that goes through the land, apples, captures different images, and from these images, recognize the apples, recognize the color of the apple that says this apple is mature, this apple is not mature, at this degree of maturity, and then you can give to the agriculture people or to the agriculture. At this moment, you have 64% of mature apples at your land. Okay, this type of problems is also solvable. Text translation is also a problem that benefits from deep learning. You know, translating a text is essentially finding a function that takes some text in Greek and translates it in some text in English. Okay, so it's very difficult because it's not just word by word; it's a whole sense of the phrase. So it's difficult. And the way to solve that, and probably you know the DeepL translator, it's probably the best. It uses this type of techniques to solve the problem using something known as transformers. Okay. You can also predict time series. If you want to predict what will be the temperature tomorrow at Heraklion, well, you can use some data of the past and say, well, main based on the pressure, on the whatever. Okay, so that's time series. Anomaly detection, I know this one very well. You know, when you want to buy something on the internet, something maybe more expensive than usual, let's say a flight to go somewhere, the bank says, this is a suspect transaction, so let's look. Okay. So it's not someone who says it's strange, it's the algorithm that detects that it might be an anomaly. Okay. Data clustering, if you have data and you say, wow, I have a lot of patients that have a disease, medical disease, can we split those patients into groups having similarities? I don't know, you have a lot of people with cancer, but lung cancer is not the same as brain cancer, is not the same as, okay? So the way of splitting automatically the data is clustering, okay? And also if you are doing some robotics, if you want to teach a robot to walk, well, you can use this type of techniques, okay? Well, what's the machine learning workflow? It's always the same. You have to select a model. That means you have to select an architecture essentially. Is it with neural networks? Is it using transformers? Is it using support vector machines, whatever? So you have to choose the architecture. After you have chosen the architecture, you have to train the model with the collected data, then test the model. That means give some new data to the model to verify that it's
correctly generalizing the information, and then deploy your model to solve something. For example, here, I'm going to have a list of images, and I use the function image identify to ask Mathematica what is inside each of those images. Behind the scenes, you have this image identify function, which is actually a neural network that has been trained in millions of images. Okay. So, sorry? Yes. 65 megabytes of data. It's not the images to train. That's terabytes of data. Maybe just to explain you why it's always the same universal principle of what is expensive is expensive. If you let's talk just 1 minute about neural networks in a very simple example. Okay. In this case, it's not bad. So imagine you have two values that enter. So you want to predict something depending on two values. Here, I don't know what we want to predict. Maybe something interesting. Well, if the person is sick or not sick. And you want to predict that from the temperature of the person and maybe, I don't know, the arterial pressure. Okay, I'm saying nonsense. So you have two variables, two input variables, and you want to say this guy is sick or it's not sick. The idea here is that this information, which is a number, okay, maybe 35.7 degrees, and I don't know, millimeters of mercury. This data enters here. There will be some computation inside. It's just a function, and it returns a class. So the function you want to construct from data is a function that goes from two numbers and returns two classes, sick, not sick. Okay? This function is unknown, and solving the machine learning problem is equivalent to find this function. Okay? Now, how do you find this function? Well, you have some experience. You have some patient data. For example, here, you know that patient number 1 had one temperature of something and a pressure for something, and you know that this person was sick. Okay? So you have a lot of patients here. You know their temperature, their pressure, and if they are sick or not. And you want to use this data to construct an approximation of this function. This function is unknown, and it will remain unknown forever. The idea is to approximate something which is acceptable to this. So I'm going to construct an approximation of f, which is f of epsilon, based on that data. And f of epsilon is actually the solution of an optimal problem, an optimization problem. The problem is find this such that f of f epsilon is in the argmin of L of, let's call this data D of D. DH among all the functions. What is saying this? It says that I'm going to minimize the mean value of the error. That means that I'm taking some data that enters and I know the answer. Okay, sorry. Thank you. I know the answer. And I'm going to adapt here some parameters such that after several runnings of passing the data and compare with the answer, I'm going to have my approximation. So the epsilon here corresponds to different weights here. Epsilon 1, 1 from the neuron 1 of the first layer to the neuron 1 of the second layer. Okay, so this is the third layer, first neuron. Second layer, second neuron, third neuron of the second layer, second neuron of the first layer. Okay, so here you have different weights. So this is epsilon 1, 2. Here is epsilon 2, 1, and 1, 2, 1. You understood, there's a weight in every single edge. And the idea is, when I say find this such that, is find those numbers. So what is expensive in computational time is find those numbers, those magical numbers that solve my optimization problem. So when you download 55 megas of data, what you are downloading is those numbers. Okay? So we already have done the job for you. And that was expensive. Creating a function image identify that given any image tries to identify the content of the image. To do that, you have to train over millions of images. That's expensive, okay? But when you already have done the expensive part, you already have those numbers, then it's free, okay? But you have already to pay that. Another type of application here using the function facial features of this image, I'm looking for faces. So the computer knows what a face is and can determine some information about those faces, like the gender, the age, the sentiment. Is the person happy? Is the person sad? And in this example here, you have those astronauts, some age, some gender, some emotion. Okay, they are all happy. You can also learn different things, like always with images here. Recognize digits.
Doesn't recognize the 5.
Sorry?
It doesn't recognize 5.
Yes, it doesn't recognize 5, maybe.
Might.
In your case. Okay.
The same.
No. I mean, it's the same data set. But what it's not the same are the coefficients there. Okay? What does that mean? That means that, remember this is a probability. This L is known as the loss function. And what it is you can approximate it by the mean error. But mean is a probability. Okay? So when you have a machine learning function and you say, is this person happy? Is this person a male? Is this person its age? It will return a probability associated to that answer. For example, in my example here, if my function f epsilon says that someone with 40 degrees and 16 thing is sick, actually it's saying that he's sick with a probability of 0.85 and not sick with a probability of 1 minus 0.85. Okay, so that's the reason why you don't have the same answer than me, because the training process, it's not the same. Why it's not the same? Well, because when you want to train here with your data, you have to take some random elements to train the function, and the other elements you haven't took for the training, you use it to test. is it a good approximation or not? So depending on the random selection of the elements of the function classified, you can get a different answer. Okay.
If you run it again,
If I run it again, it may recognize something different. Yes. So this is the classification problem. You have here the learning curve, and the idea is this function goes decreasing. It is the error. Okay. In this case, I get the same result, but the idea is that if you run it several times, there will be a moment that you can have different things. Yes?
can you classify it from the, so that you can say the correct random elements? You know, just prioritize some random
So your question is there an optimal way of choosing the splitting of the data? It's a good question. In theory, I think no. In theory, I think no, because, well, I mean, yes, the optimal is really random. That should be the optimal. I don't know if your question is in that sense. When you use random numbers in the computer, it's not really random, it's pseudo-random. That was your question?
Yes, I know that the computer is not, it is random, but maybe the computer characterizes the randomness in such a way that it's not so random.
Yes. Maybe the answer will come in some years with quantum computing. Because in quantum computing, you have truly randomness and truly generation of random numbers. So there are some fields mixing quantum machine learning. So yeah, maybe very soon. Actually, if some of you are young, that could be a good way of getting a job later.
Wolfram Language stands, but
Yes. At Wolfram we have recently, it's available on the Wolfram page. Quantum computing seminar. It was nice. It was maybe 5 lectures or something. But more to come in future years. Well, the Wolfram language make it so easy. It's divided by task. If you want to classify a sentiment, you say classify sentiment, and you give these phrases. This is a positive sentiment, a negative sentiment. You can classify something as spam. Yes, spam, no spam. You can classify a Facebook topic or an Instagram topic.
here also, I'm hoping we make the binary.
No, this is not binary. Yes.
With the function, it has a probability.
Yes.
We make over 50% or over.
Well, if the probability of getting C here is bigger than 50%, it will return C. If it's lower than 50%, it will return no. Okay.
Then there's no way to change this.
Well, in the case of two classes, that's the best to do. It's known as the theorem. It's known as the best approximation base. Something like if you write the best base approximator, you will find this rule. But if you have more than one class, for example, here in the Facebook topic, actually you are cutting the interval 0, 1 into n subsets of equal probability. If that's interesting, it's actually in the notebook. If you know that there is some bias on your data, you can actually introduce that knowledge to increase the quality of the grade. Okay? I think there's an example in the notebooks later with, in a case you have more women than men. You can detect the language from text using language identify. You can highlight different elements of text. Is this a verb? Is this a name? Is this an adjective? You can find parts of speak. For example, here, I want to find all the quantities in the Wikipedia page of the moon. Okay. So the moon, probably something about the radius of the moon, something about the weight of the moon. All those quantities is what I'm interested in. Okay. It's computing. This is also interesting. I am going to go faster. But the idea is here, you have a question based on text, and you want to answer that question from the Wikipedia page of the content. So, who was the architect of the Sagrada Familia? You import all the articles containing those keywords, and then you use find textual answer to get the answer of this question. And if you evaluate it here, you will get obviously Gaudi. Thank you. Okay, it takes some time. It's the first time for things. Another type of things you can do is to use an already trained model, and you can visit and actually I encourage you to visit the site of Wolfram neural net repository. In this Wolfram neural net repository, you can have access to several neural networks already trained. So we have already paid for you to perform different tasks. Task with audio, task with image, numeric, text, video. Let's try something with audio. For example, here, this is speech detection net. This is represent a sequence as a vector. Don't worry, I'm not going to use the sound. Deep speak, you have different things, okay? Task type, audio analysis maybe, okay, or question answering. You probably will find something interesting for you. Recently, there's a company who solved a very important problem, which is a problem in biochemistry. The problem in biochemistry was, given the sequence of amino acids composing a particular braid of DNA, you want to know how the geometry of the protein associated to that sequence will be. So the idea is you get some letters, C, T, A, C, C, G, something else. And from that, you want to predict what will be the geometry, the shape of the protein. And that's important because the geometry of the protein will affect its behavior. If you take hemoglobin, for example, the shape of the hemoglobin, okay, you have hemoglobin alpha, hemoglobin beta. Well, the red blood cell allows the red blood cell to transport oxygen and carbon dioxide. Okay, so the shape is very important, and mutations in the shape. So it was a difficult problem. It has been solved by this company, and it's one of the greatest things of last year. Okay, so I get my answer. No, it was using their own technology. They are based in England. The company
the name of the company is Alpha 9. Or something like that. They have solved already other problems. Like if you saw in Netflix it's very interesting to see actually. It's AlphaGo or AlphaZero. AlphaGo, I think. It's an incredible moment because you have Lisidor, who was the number one Go player in the world. Number one. The number two, I think, is 15 levels down Lisidor. And they were in Korea. And Lisidor was playing against the computer, AlphaGo. And there's a particular moment, very nice. You know, Go is a very simple game. You have like a chess, and the person who wins is the person who captures the biggest area. You have two colors, black and white, and the person who takes the largest area wins the game. And what is nice in that movie is that at one moment, the computer is doing something very strange. The commenter, nobody was understanding why the computer was doing that movements. And at one moment, there's a structure that emerges after the different steps. And what is incredible is that the computer, in a certain sense, tells you a new strategy to game the game, which was you don't need to game the game. Okay, no, game the game. To win, yeah, I was saying to win the game by a lot of by the big amount of points. One is enough. So it's incredible that the computer wins with just one. So it was very precise. Okay, so this is a very nice video. This is another type of task. So I am importing one neural net from the neural net repository, which is color net image coloration. I give a black and white image, and I get a colorized image as an output. Okay. So if you have your grandparents' photos somewhere, you can try this. Essentially, they are three main paradigms of machine learning and subparadigm. Let's make it simple. Supervised learning, you have the answers. You have the input and the output. That's supervised learning. On supervised learning, you only have inputs. You don't know the correct answer. The first one is expensive because having the correct answer means that someone has to answer correctly the questions. So that's why it's less and less used compared to unsupervised learning. It's less expensive. And reinforcement learning is when you give some feedback to the learner, typically for robotics. If you want to learn to a robot to walk, if the robot do something bad, bah! Okay. If it's done well, then you give it a reward. That's the idea. Automatic machine learning. Well, this is not very interesting. Progress check. Okay, so that was the first notebook. The second notebook is on supervised learning. Classify, predict. Here's a simple example. If you want to classify this, you give the training data, an image, arrow, the class. And this constructs a predictor function, which is called day-night. And the useful thing is that you can now test it on new data to see the generalization power of that algorithm, okay? And this last example here is important because of what we were saying. It says that with a probability of almost 100, it is night, and with a very tiny probability is day,
So that's the probabilistic interpretation of that. If you want to get the data, you can get it from experimental data. If you work in a lab of physics, you can get it from the internet, from any web page, Twitter, if you want to analyze tweets. And you use the function import. With import, you can import a lot of different types of formats of files. Maybe 200 or something like that. If you say import formats, this is all the formats that you can import directly to Mathematica. Directly, okay? They are 234 native formats we can work with. If I want to import the images of the Wolfram website, I say import this website, the images. And I get the answer as a list of images. I can also import a specific file if I have my data in a CSV file, an Excel file, yes? That's a good question. It's actually a theoretical question. It has an answer. Let me just do it. Sorry, I was thinking about it. Okay. So there's a theoretical answer to that question. The best, let me, this is not my computer, so I don't have it here, but there's an estimate. You have a formula. I can, the reference is a book known as, the title is Understanding Machine Learning. The authors are Shai Ben David and Shai Shatz. Okay? So this is a good reference. In one chapter, you have this expression that says how many how many data you know to ensure some quality of the algorithm. What's nice is this an exponential bound, so you don't need infinite quantity, something reasonable. So there's a theoretical answer to that question.
And also, any results I don't get the results of computable interval. Doesn't say that it's percent probability with an interval.
I see. Actually, yes, you can. I don't remember how to do it here, but it is in a very good book that is actually free in the Wolfram website. It's one of our staff who wrote the book. It's Introduction to Machine Learning by Etienne Bernard. So this book is very, very well written, and in those examples, the examples of the book, you will find the answer to that question. Yes. For the emails, if you have the emails saved in a folder, you can do it this way. You just say import all the files in a folder. But if you want to import the email from your own account, let's say Gmail account, you have first to configure a link between Wolfram and Gmail. It can be done through the preferences. Here you go to preferences and then internet and mail settings. So if you want to bring your emails from Gmail, you have to put here, that's the port number essentially. and it is the protocol, and of course your email address and your password.
Okay, that's not what I
Sure.
meant, but it's okay. I meant that.
Okay. For example, if you say, I want to recover all the emails of the faculty of this university. Yes, this can be done. It's not easy because we are working on a team to work on that problem. Why is difficult? It's difficult if you want to do it as a generic tool. That means that works for any university. But if you want to do it for a specific web page for which the structure is the same and never changes, this is more easy. But if you want to do a general tool that works with every website, because each website has a structure, and if you want to access to the data, it depends on how it is constructed. Not because sometimes you will have a button with stuff, so you have to click on stuff and then go to the list. Sometimes it's not a list, but it's an image. So not with every. It works with Gmail. It works with Outlook, at least. I haven't tried another one, but at least with those it works. Okay, so in supervised learning, you have to ensure that data is labeled. The label is the answer. So you have the input and you have the correct answer, which is the label. Here, for example, this is a classical one. It was a guy who tried to predict the species of flowers depending on some physical measures of the flower. The length of the petal, the width of the petal. This is old, huh? This was solved long time ago, but it is maybe the most known example. It is the iris of Fisher iris. So if you go on Google and look for 25 minutes, thank you. If you look for Fisher iris, you will find a lot of information of that. So for values, petal length, sepal width, petal width, and that's okay. Images. Okay, maybe try this exercise on your own. Sneaker or boot. Here you have a data set containing a lot of images for little images of t-shirts, of boots, of shoes, of different clothes. And the idea is to construct, for example, let's take training data from 1 to 5. The data is this type, so this is a t-shirt or something, so it's in class number 2. This is a shoe, so it's in class number 9. This is maybe something else, so it's in class number 6, class number 0, class number 3. Okay, so what you want to do is to train the computer to predict and to learn to predict what type of cloth it is. Is it a shoe? Is it a t-shirt? Okay. And the idea is to do that by your own using the classify function. Okay. So for example, C will be my classificator. So classify training data. That's all I have to do. It's very easy. You will see the training process. So the learning curve has to have its shape in order to ensure that error is increasing. Here, if you want to do something which is more expensive, you can take the advantage of GPU. If you have a NVIDIA GPU, okay? So it only works with NVIDIA, at least for the moment. Maybe later we can do something. But for the moment, it only works with NVIDIA. So if you have a GPU NVIDIA, you can say here an option which is target device GPU, okay? So instead of doing this, you say classify. And that will accelerate the process of learning. Okay? The more data you have, or the more complex the data is, the more time you will need to solve the problem. Okay? There is another thing which is important, and maybe that's my message to you for this session. There are some basic principles in machine learning. One of those is the yeah, in English we say garbage in, garbage out. Okay, so if the data has some bias, if the data has some errors related to the acquisition or something, that will be reflected on the prediction. Okay, if you train your model in data which is not clean, let's say, then you can't wait that you can't expect that your model will be good enough. And there's another principle known as the no free lunch theorem. So the no free lunch theorem is a theoretical result, very deep, that says that it can exist a machine learning algorithm capable to solve all the machine learning problems. It can exist. That means that there will be always several machine learning algorithms to specific problems. Okay. I think the computer is blocked. Yeah, well, I'm going to force quit. Yeah, thank you, thank you. Thank you. Do you have any other question for the moment? No? Control open. Let's go to unsupervised learning because this one is also funny. Feature extraction. When you give an image as an input, the computer doesn't know how to interpret that image. An image is a matrix of pixels, and each pixel has 3 values that corresponds to the red, green, blue values. So you have to transform that image into a vector, okay? A numerical vector. That's the reason we use encoders. Encoders allow you to transform any type of input. It can be images, it can be text, it can be something mixed into a vector. Okay? You need to do that step because the model, which is something like this, only knows how to compute with numbers. Okay?
So you have an image, you have a text, you have to project that into a vector space to get a vector, and then you can start here.
So that's the feature extraction. Let me show you here some examples. If you have the text that says, the cat is gray, my cat is fast, you can segment that into characters, you can segment that into words, and you can use some very known feature extractors like TF-IDF that constructs from a text a vector. So when I have a large cat, this constructs a matrix that represents the text I enter. Here, the cat is gray, my cat is fast, this dog is scary, the big dog are sentences represented by those vectors in 3 dimensions. Okay? So here, 3 dimension is because I use the dimension reduced vector, because it's not, it's then larger dimension. You can extract the features of a composed element, here a text and an image. And you can classify with some properties and options of the feature extractor. Here I want to put every single letter in capital and remove the accents and segment using words. And now if I say this is a dog, since I use those feature extractors, this returns the correct class. Okay. Maybe a more interesting example here about feature extraction. If you have some images of dogs like this, you can create a feature extraction of those images. That means that every image in this data set will be represented by a vector. Now, with this extractor, we can measure if 2 elements are close or are far from each other. Okay, so for example, here, those 2 have a distance in the feature space of 15, and these 2 have a distance of 49. It is normal because those 2 are similar or are more similar than those 2. Okay, so using these techniques, you can actually give a sense of the intuitive notion of those 2 dogs are more similar than those 2 dogs. Yes?
In this case,
Well, they are relative to the data set. So it depends on the data set. I think actually it's the next.
Is the difference between 45 and 50 the same as that?
Yeah, so it will depend on this answer. So feature space plot will take all the images of the data set and put together those who are close and those who are far relative to each other in the data set. So here you can see that dogs that are similar to each other are grouped together. Okay, so here it's something is small is compared to the diameter. What is the diameter here? The diameter is the maximal distance between any 2 points, any 2 images here. So it will depend to that diameter. The notion of close or far.
Smaller number for the first 2 and a bigger for the second 2, is better than
No, it means no.
maybe 60 and 120.
Yes.
It gave you 15 and 49. So my machine.
No, it's not the correct way of interpreting the thing. It's always related to the whole data set, okay? The complete data set. So if with the complete data set, 2 points are more far in distance than 2 other points, that means that inside this data set, those 2 images are more similar or less similar.
But we have the same data.
Yeah, if we have the same data set, we will have similar distances of the same order. Okay. Here, the exact value won't be the same, but the order will be the same because we have the same full data set. Okay? And the same transformer and the same. If you do the same in different machines, the order will be preserved. In this case, there's no difference. Okay.
Okay. So feature space plots have grouped together those dots in this nice picture. Okay, and you can see that we have those 2 groups. Okay, I don't know what's the name of those. Those are Labrador. Sorry?
There's a photo of the woman.
With a dot.
No, there's a photo of the woman.
Ah, yeah? Well, that's a mistake. I don't know. It's not me who collect the data. She's holding a dot, no? Oh.
I'm happy to avoid the political mistake.
Okay, how to get those clusters? Well, here the idea is to conform images. This is a very useful function. Why? Because here the size of the image will be a vector corresponding to the dimensions of the image. If you have, I don't know, 300 pixels by 500 pixels, here you have a vector of size 300 by times 500. Okay, so it's a huge thing that enters into the neural net. The information propagates inside, and at the end you get the result. So before training, you have to get all the images the same size. That's essential.
The same quality.
It's not related to quality, it's more related, well,
Yes, it's more or less related to quality because more pixels means more resolution. But actually here it's more, they have to have the same dimension.
why they have the same dimension? Because this dimension is not changing. I need 2 here always. Okay. How to get those clusters, anomaly detection. Maybe that's an interesting example to show before ending. So digit images is the MNIST dataset.
The MNIST dataset is a dataset with handwritten numbers. And here we want to train an anomaly detection
predictor function. So this function is actually learning a probability distribution
of what means to be normal and what means to be
anomalous. Okay. It is not related to humans, no.
Yeah, we have this anomaly detector function. You can see that it's a distribution.
And now you can try to evaluate the function on a new data set. And the anomalies are those images with the color negate.
Okay. You can do the same, for example, now in the watch, you can follow your cardiac activity. So there are some specific patterns associated to specific disease, cardiac disease. So detecting an anomaly and classifying the anomaly allows the watch to say, well, you are having a heart disease.
You can learn from any kind of data, and that's here you have an example with colors. I'm learning the distribution of colors, and now I want to generate 20 new colors generated from this distribution. Okay, so I am not getting some red or some green color. I mean, I can get those, but with a very few probability. Okay, so if I ask 20 new colors, learn from this distribution of colors, I get this. Okay, so what is important for you, I think, in the machine learning lecture is to try to identify on your own field, if you are a mechanical engineer, if you are a biologist, if you are XY, to see what kind of problems can be solved using these techniques in your own field. And almost any field can be can have these benefits. This one is nice too, if you want to generate random images similar to Van Gogh paintings. Okay? You can also generate faces. It's a more sophisticated example. Probably you know that every single technology comes with some part of responsibility. No? Probably you saw recently that there was we call that deep fake. So deep fake video, you can create a video with almost any face. Recently was Zelensky, I think. So maybe the Russians create a video with, using the face and the voice. You can imitate the voice, you can imitate the face. Of course, you can use the same technology for much more nice purposes. But it's not the technology, the problem is the human always, who needs to get some maturity level to use the technology. It's like an arm, you can eat by hunting or you can kill somebody. It's not the technology the problem, it's the person. So here some new images similar to Van Gogh paintings. They are random. It's just like random pixels, okay? But they look similar to Van Gogh. You can use different types of methods to do the same. Yes. Thank you. Maybe let's end with this: the missing data. This is a problem in the applied fields like applied physics, or if you want to work with data, data is expensive and sometimes you miss some value. For example, the sensor wasn't working from t equals 1 to t equals 2, and you have some data with the temperature missing. But you have the other values. You have the value of the pressure, you have the value of the quantity of, I don't know, whatever. And since collecting that data was expensive, you don't want just to say, okay, temperature is missing, let's put everything into garbage.
So you just copy some of the data.
Well, it can be done like that, but you can use machine learning to predict the missing data. And these type of things have the Bayesian property. So Bayesian property says, in a simple way, something like the node. Let me give you an example. Imagine you are in the street and you see someone running. And I ask you why that person is running. Tell me something. why the person was running. Sorry? Okay, he's stressed because he's going to miss the bus. Yeah, that can be a solution. But if I tell you that at the end of the street there's a lion, what do you think he was from? What's a lion? That's the Bayesian thinking. If you add information that you know of your phenomena to the model doesn't take any value. It will take more probable values. Okay? If you add information, the model recovers that information to give a more accurate answer. Okay? So that's the idea here. Using the data, you can try to predict the missing ones. And you have different techniques here. You can see that in detail. Okay? But think about when you will have missing data. Maybe. Okay? Okay. Well, thank you very much. It was a real pleasure to be with you. See you soon, I hope. Here or in France or in England. Who knows? Okay. Thank you. I don't know if you want to stop.
Okay, that's okay. So let me thank again Mario and Alex for taking their time and make this wonderful introduction to exotic uses of Mathematica. In fact, I'm not a machine learning person, so I hope to train Mathematica to cook my coffee to perfection from today, tomorrow. And well, we are a community here. Mathematica is expensive, and we have to show that we want it. So we have to use it, and we have to produce things and say that it's worthwhile using it here at the National Technical University of Athens. And I hope that we will form a community and exchange ideas and see what we can do more with this wonderful piece of software. And well, that's from me. Thank you all for participating. I don't know if Alex was coming to tell us something before we go home.
I just wanted to say thank you very much for attending and for being here. It's 6 o'clock in the evening. You've been here all day, and I just wanted to say thank you to Mario because it's been a very long day for him as well. So that's the plan. At the moment, is okay. We are providing licenses, access to the Mathematica system of Mathematica Online. The idea is to, in fact, to create a much bigger community and make sure that students at the university have access and start using the software, because that's something you will eventually, unless you are planning on becoming academics and maybe do some research or teaching here, but also that's a piece of software that you will find in, later on in life. So I think it's a good investment. For Mario's case, I think you've been using it since you were.
Since I was in high school, I think.
In high school, so you've been using it for a long time. And we are Wolfram is a very innovative company as well. So we are keep trying to push the boundaries, and we are still obviously adding more features. So that's why you might see some more new release in the next few weeks, and then you see another release by the end of the year. So that's more the kind of software that we provide, and then we don't touch for the next 10 years, and then we might come back and say, okay, we are going to add some new features. There's a lot of people working on this product. We haven't shown too much of Mathematica Online and how to deploy to the cloud, which I think is a pretty convenient way to share work, to share a document and share interactivity documents. But I just wanted to say thank you very much for having us. It's the first time in Greece for me, so that was also a very good excuse to come over. I think it was the same thing for Mario. And we are going to obviously meet at the university in the next few days. But that would be nice to obviously come back in the future and maybe the next things, obviously, we have the events on Thursday. Also, I think we are going to maybe organize another online seminar for the architecture school as well, because we have a French guy who's an architect who lives in Athens and he's been using Mathematica for many years, so he's happy to share his experience. And yeah, feel free to get in touch with us if you have any queries, any questions, if you are looking for maybe some of you guys internship, if you want to, the headquarters are based in America. Stephen Wolfram works on the Boston office. So there's plenty of opportunities as well for you guys, the younger generation, if you want to work with us or get involved in the project. Okay, so thank you very much. Have a nice evening, and hopefully when we come back, you will be all mathematical experts, and that would be interesting. We haven't shown some of the resources as well, the demonstration websites.
Yes.
We've got so much content online that we've got no excuse not to become a very good Mathematica user. We spend a lot of time and effort to make sure we've got plenty of resources.
Meanwhile, let me comment that visit the homepage of the event next couple of days. We post event data like notebooks. They're kind enough to have them online, whatever. And possibly the links to the videos. And maybe more.
Yeah, I think that's really
This is again. We post also the information about Thursday's event.
Yeah. But for the younger generation, we've got lots of mathematical users around here, and I think we should try to, pick their brain and take as much as we can. Okay. All right. So thank you very much. There's a few pens, a few stickers, and things here. Make sure you take them away, so I don't have to carry them all week. And then we hope to see you soon. Okay. Have a nice evening.
Okay, thank you very much. Thanks for attending. And feel free to ask any question and to get in touch with us in the future. Have a nice evening.
Yes, completely. The function you can look in the documentation is net chain. Yes, net chain. Net chain is the most basic one, but you will see the links to the more advanced. Net chain essentially is the your neural network. You say, okay, I want the first layer, count those layers.
Years ago. So,
With